The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so let's get started. A lot of stuff happened in the last lecture, so I'll spend a little bit more time to review what we talked, what are the key points here. So what we did in the last lecture is to ask the question, what are the electron energy levels in a periodic potential? And that's really the periodic means we'll start thinking about the crystals. And we started with one-dimensional simple pictures where I have periodic arrangement of atoms. And so if you recall before last lecture, what we're considering really are confined states of an atom, of a molecule, where the wave function is spatially just around the atom, around the molecule, right? And in this periodic structure, what could happen is the wave function that originally electron belong to an atom, now they have space to flex their wave function, muscles, right? It goes through the whole crystal. And in that expression, what we have is we use an extended wave of different wave vectors, right? And so each of those wave vectors represent, say, a wave function. And if I have n atoms, and the wave vector is every 2 pi, k times a every 2 pi, I have a repeating. So at the end, I'm drawing only 2 pi. In fact, I'm drawing from negative pi to plus pi. And I'll give you the rationale today why we draw this way. And then it's important to recognize that between minus pi over a to plus pi over a, we have a total of n points because I have n atoms in this periodic direction. And each point, of course, represent a quantum state, except I do not have the spin included. So if I have n points, in fact, I have 2n, so it's symmetric, right? From minus pi over a to plus pi over a. So I only draw, you see, I only draw the 1/2 of it, right? And if I count from here to here, there are really 2n quantum states, right? And with that, I say if I give hydrogen as an example, if I could arrange them in one-dimensional periodic fashion, then because each hydrogen has 1 electron, and at the absolute 0 temperature, the lowest energy level fills, and you will fill to the middle of the band, right? And if I have 3 electrons, lithium, you'll fill to here. It fills to the middle of the band. And in that case, those are the metals where at the non-zero temperature, there are some, if there's very little energy, you can move around. Those electrons near the top, where the uppermost energy level that filled with electron, this is called the Fermi level. Right? At the absolute T, the uppermost energy level where electrons are at the Fermi level. And if you read the different books, sometimes people will call at the non-zero temperature, they'll say that's also Fermi level. But to say a more better way is at non-zero temperature, this one can shift a little bit around that position, and that's say it's better call them chemical potential. Okay, so different books, sometimes they distinguish, sometimes they do not. I had a student came to me and say, what is, say, in electrical engineering, for example, if you read electronics, they'll always call that Fermi level. Non-zero temperature is always called Fermi level. Okay? And so this is, of course, it fills to the top. Then there is a gap in energy. That means no electrons can exist with that specific energy in the crystal. So no waves allowed. And so if I have 2 electrons, then again at 0, you will fill to the uppermost of the lowest band there, right? And now because there's a gap, electron does not have enough energy to go to the next level if that gap is large. So for a large gap, electron cannot move because there's no quantum state. Now everything is filled here. There's no more quantum state this electron can move to. So the Fermi exclusion principle say you can't have more than 1 electron per quantum state. So this is the case where there are electrons in the material. They're always a charge, right? But you get the insulator. There's low electric conduction. So this is the insulator. And of course, we spend most of the time on this one-dimensional, say, lattice Chen model. And if you go to 3D, which we'll talk more today, you look at each direction of the crystal, you can say a different periodicity. And different periodicity also means the bonding between the atoms in that specific direction, the force is different, right? And so you'll see a different band structure. I'm just hand-wavily drawing this, right? So this is A1 is one specific direction with that periodicity A1. And another crystallographic direction could be A2. And in fact, there are many crystallographic directions in the crystal. So ideally, you know everything. You know each direction, what are the energy diagram, energy of the charge. And here I'm drawing 2 directions. And now, say, this is the minimum point here. This is, say, the maximum point in the first band here. And again, the band gap, this is the gap here. But when I talk about the semiconductor, I'm talking about the absolute gap, meaning this is the highest point where the electron fills, and lowest point that's empty, and there is a separation in energy. So in this region, there's no, in this region here, there's no electron in the material, in the crystal, that has, say, could have those energy. That's quantum mechanically forbidden, right? That's what a real insulator, like a glass or quartz, if you think about crystalline form of glass, right? This is where electric insulator has a very large band gap. And if this band gap is small, is not that large, let's say silicon is 1.1 electron volt, it becomes a semiconductor. And for semiconductors, we have different scenario where this lowest energy point, maximum energy point, they do not align to the same wave vector. That's the case for silicon, and that's an indirect gap semiconductor. So we have different type of semiconductors. We have direct gap. We have indirect gap. Right. So direct gap is when the conduction and the valence band, so the upper band we say conduction, and lower band is valence. So they are happening, the minimum and maximum is at the same wave vector, while indirect is different. It could be here is the energy, here is the wave vector, and they may happen at different wave vectors. Okay, and this makes an important distinction between gallium arsenide, which is a direct gap semiconductor with a band gap of 1.4 electron volt, and silicon, which is an indirect gap semiconductor with a band gap of 1.1. And you see most computer chips are made of silicon, but most lasers, pointers, made of gallium arsenide. Like, say, this one, when you want to make a light active device, direct gap is usually better because you need a light. Light itself do not have much momentum. So here, K is the momentum. So H bar K is what we call crystal momentum. It has some difference from the real momentum of the electrons, but say we're not getting into that subtle difference. In typical way, you can think is this is when I think about momentum conservation of say a light comes in, interact with the electron. I use H bar K of the electron in the crystal. I'll use H bar K for the photon, right? Now, the difference, of course, remember K is 2 pi lambda, that's magnitude, right? So if you look at here in crystal, my lattice constant, this is pi over A, that's angstrom in lambda wavelength. And photon lambda is micron, so the photon momentum is almost negligible. Very small, and the electron momentum in this case, if they're different, they're very large. That's why indirect semiconductors do not absorb well. Okay, do not absorb light well. And that's the biggest problem when you make silicon solar cells. You need a lot of materials to absorb this photon. Okay, so this is the direct gap, indirect gap. And a little bit more terminology for semiconductors, right? And if I do not put impurities, do not put, say, any, other atoms, silicon, for example, at absolute zero temperature, the electrons will be here. That's the uppermost energy level. That's at the absolute zero temperature, the Fermi level, where the Fermi level is. Okay, and now at non-zero temperature, some electron gain enough thermal energy because of the Boltzmann statistics. There always the electron has a distribution, and some electron move from here to here, and that leave behind empty states. And because of empty states, the electron here, few electron here, are very happy because there are a lot of empty states. Many electron here are also happy because now they finally have a little bit of room to wiggle, right? So the ones on the bottom, rather than describing the motion of all those electrons, right, feel the electron, equivalent terminology is describe the motion of those empty states. That's holes. And holes, when I think about holes, energy is increasing this way, because it's the negative of the electron. When I think about electrons, the energy is increasing this way. So when I look at this band diagram, when I think about electron hole, I actually say this direction is the energy increasing for hole. That's the energy increasing for electron. So we have electrons. We have holes. And here, where the electron move is the conduction band. And where the hole move, this one is the valence band. Okay. And if it's a true intrinsic semiconductor without doping, at absolute zero, it's an insulator. Because it's frozen, all the charge is here, and there's no mobile charge. So there are no empty states for the electron to move. But say normally, I do not deal with when I use a semiconductor device, I want to have a specific either electron as a majority or hole as a majority. So I dope it. So that's intrinsic, extrinsic semiconductor difference. So we have intrinsic, that's when we do not dope it. And extrinsic, when we dope it. And when we dope, we can dope the N-type when I put the phosphor, or I dope P-type. So those are the semiconductors. And one more thing I want to introduce. This is if I look at the energy electron at the bottom or hole at the top, right? And in fact, that's the bottom of hole, right? And when I do the, because this is at the minimum maximum point, so most of the time the charge in semiconductor, when you do not deal with the heavily doped, they are only at the bottom or top region there. And because it's a minimum maximum, so I can use approximation. I can expand the potential, electrical energy, right, around the minimum maximum. So if I do an expansion, typical expansion, so energy as a function of K, and I'm writing 1D. You can say K in a real crystal in each crystallographic direction has a K, right? So I'm not writing in vector form, but say I can expand that. Let's say here, this is a EC, conduction band edge. This is a K0, right? That's where the minimum happens. So I'm going to expand this as a E, say K0. That's the lowest, the first term of expansion. And the second term, dE dk K0 and K minus K0. And the next term is dE dk square and K minus K0 square, right? Okay? So this term, because the maximum minimum is 0, as long as I do not have a sharp turn-in, right? If it's a linear profile, I cannot make that approximation. So normally this is 0. And this one, let me write it into a form that's nicer. So I could write this h squared K minus K0 squared and divided by, say, 2m, m as m star. So just a symbol, right? So this m star, because I have a h bar square, so I will have in the denominator, I will add the h bar square and the d e dk square. Do I? Okay, right? So you can say this m star is a second order derivative of this curve at the bottom, right? So if it's the m star is large, how is that shape looking like? Flat, right? M star is small, that shape, that parabola, local parabola, is narrow. M star is large, the local parabola is fat, right? So this mass is like in fact, it has a unit of mass. If I write a free electron, this is hk is the momentum divided by 2m, that's the kinetic energy, right? So by writing into this, I introduce this m star as the effective mass and using this effective mass, this is hk, that's more like a kinetic energy term, and this is a potential energy term. So I can describe now the electron in this small band they transport as essentially inside the crystal as a free electron, but with a different mass, m star. And in fact, now you can say, because this k in a real crystal in different direction is different, right? So the mass in different direction is different. So in fact, many times this m star is written as a tensor rather than just a single value there. And that depends on different materials. So this is both overview of last lecture and also some extension in terms of the effective mass. And where I'm going today is continue this 3D picture. Now we have 1D picture, we're going 3D, right? So in the 3D, I want to first talk about the crystal structure to get more familiar. And then I will talk about what are the bonding between the atoms that hold the crystal together. And finally, we'll use a mathematical terminology is how we can, it's a periodic function in 3D, and what's the corresponding Fourier transform, right? We did a one-dimensional, we say this K essentially are the Fourier transform. So this is where we're going today. Let's look at the crystal structures first. And at the end of the lecture, I'll show the best is by looking at the more visually. I can't draw that way. Also, I'll use 2D as an example, but at the end, we'll look at the 3D online. Okay? So crystals can be described. The most important characteristics of crystal is periodicity, periodic arrangement of atoms, right? And they have different atoms putting into the same structure. So a crystal we can describe as a lattice, which is a mathematical concept, plus basis. So lattice is a periodic arrangement of points in space, and it's a mathematical concept. No devoid of any real materials. And by doing that, you can actually classify different structures of these periodic points. So let's take a look at a simple 2D, like I said. And 2D, but there is a center point. 2D structure, periodic arrangement. And we introduce a few basic terminology. One is primitive lattice vector. So in 3D will be A1, A2, A3. In 2D, of course, you only have 2. And what is a primitive lattice vector? It's a set of vector. With that, I can use the linear combination to reach all other points by integers. So I can use this primitive lattice vector to construct a translation vector, N1, A1, plus N2, A2, plus N3, A3. Well, N1, N2, N3 are integers. Okay, So this is the primitive lattice vector. And the problem is if I look at this 2D, I have different ways to choose the primitive lattice vector. Here is one way. If I have this one and this one, if you look at this, I can use this tool and the linear combination of this tool reach any other points, right? So this is, let's say, A1, and this is the A2. And of course, you could also choose a different one. You can choose this one and this one, right? So one of the challenges is how to narrow down our choice, how to uniquely define this choice of primitive lattice vectors. The other is a conventional unit cell. So primitive lattice vector, those vectors will form a unit area or unit volume, right? So in 2D is by this unit area. If I choose this is my unit area, and I just repeat it, I will pile up the 2D space without any voids. And similarly, in 3D, I choose my primitive, this unit vector form a volume. That's a primitive unit cell. So this will form a primitive unit cell. Right? And so this is the one choice of the vectors. And the other choice is a conventional. You can say unit cell. Okay? And say if you look at this, it probably is much easier if you choose this as your unit cell, right? It looks more regular. And if you look at the difference of a primitive unit cell and a conventional unit cell, a primitive unit cell, each of the cell has only one lattice point, equivalently. This is because although this primitive unit cell has 4 lattice points, each of this lattice point is shared by 4 unit cells. So each the lattice point is 1/4. You add up, it's 1 point, 1 lattice point in 1 primitive unit cell. But if I take this conventional one, you can say this one is shared by 4. So 1/4, 1/4. That's in my current drawing. There are 2 points, 2 lattice points, in 1 conventional unit cell. Okay. And like I said, one of the challenge is even if I take a primitive unit cell, each of the cell has 1 lattice point, I do not have a unique way. The way I have many choices. So there is a cumbersome but a unique way to do it, to define a primitive unit cell. And this is a wigner-seitz construction. So let me extend this drawing here. I will extend to this side so to make it clear. Right? So one way to construct this is to take any of this lattice point. Right? Here is the lattice point. I collect all the neighboring lattice points. So I collect all the neighboring points. Right? And then I take the bisect of those points here, of these lines. So this is a bisect. And here is a bisect. And here is a bisect. And you have another point here. And it turns out this one is not a regular cell. It doesn't look very good, right? But it's unique. Because any crystal structure, I can take a lattice point, I collect all the neighboring points, I take bisects, and the minimum volume, in this case of area, the form, is a primitive unit cell. And I can use that to stack together and form and fill the whole space without the voids. Right? So it's not the easiest construction, but it's a unique construction. And this is called wigner-seitz construction. Wigner-seitz unit cell or Wigner-seitz cell, because it's always this construction always gives you a unit cell. Okay, so this unit cell gives you, now we have the primitive lattice vector, the primitive unit cell, and as I said, this lattice is a mathematical concept, right? So there are require different symmetry. The most in 3D, for example, the easiest is triclinic unit cell that I can stack and form the whole space, fill the whole space. So there's no symmetry. The angle, there's no 90 degree. And the lattice constant between here, the unit cell, the lattice constant in each direction are different. So this is a general one, right? But then there are different symmetry. If you add the symmetries, it turns out there are only a total of 14 types of the crystal lattice. And I will defer this later on to show you on computer. And these are the 14 times also called the Bravas lattice. Okay? So we'll look at this in computer later on. And one more convention of this lattice, the mathematical description, is different crystallographic planes, right? So if I take a cubic structure, a unit cell that's made of cube, right? My question is how I would denote different faces, different crystallographic directions, right? And the different crystallographic planes. And the convention that's usually used in define the crystallographic planes is, let's say this is a 3D. I have A1, A2, A3, right? And I have any crystallographic plane, for example, from here going here. This is the middle point. And I could have this point. So this form a crystallographic plane, right? Any of those. So if I have a plane that intersects this within the unit cell, let's say at one point, A1 direction, I have an intersection point, A2, A3. Let me give you an arbitrary number as an example. So this is 0.8 in terms of the total length of unit cell. And here is 0.4, and here is 0.6. Right? This is a plane within that cube there. And the way I label this plane is this Miller index method. And you take first step is you take a reciprocal of those numbers. The reciprocal is 0.8, 0.4, right? And then say 0.6. you take say inverse of this intersect, and then you reduce this to integers. You multiply by the common factors, right? So if we multiply, reduce this to integer, I multiply by 2.4, and I get a 3, 6, 4. So that's the crystallographic plane that we just draw. This is the convention. Okay, and you see that's a pretty cumbersome why you take an inverse, right? That's one way to think about this is if I look at this cube again, for example, this surface here, right? And if I do not take an inverse, you see my intersect, say this is a A1, this is a A2, and this is a A3. And if I look at this surface here, that intersect here is 1, and the other two directions is infinite, right? So this surface will be intersect is 1, infinite, infinite. Okay, and I guess people don't like an infinite, so take an inverse, and that becomes 1, 0, 0 plane. Okay, so that's just the convention of denoting specific crystallographic planes. Okay, now here is so far is mathematics. We see the lattice point is abstract. There's no mass, right? Just periodic array, and there are 14 types. And but we have so many variations in real world, different crystals, right? Different materials. So structurally, among the 14 type, the difference is really at each lattice point, what do you put there, right? What do you put there at each lattice point is a basis. Okay, and you can put a single atom at each lattice point. You can put 2 atoms at each lattice point, or put a molecule at each lattice point, right? So salt is a common. Salt is among this 14 types later on is a face center cubic. It's a cubic structure with 1 atom at the face. But say at each of those lattice points, you actually put a sodium and a chloride atom. Not well. So okay, each lattice point doesn't mean they occupy the same space. It's just periodically you can say, okay, this is a sodium, and in another direction you have chloride. You just repeat that for each lattice point. This will become more clear later on as we look at the computer. Okay, I can't draw very well, so I will rely on that. And similarly, silicon crystal, right? And silicon crystal, it turns out, say at each lattice point, you put 2 silicon, and silicon and silicon. So again, that's even at say the same everywhere is a silicon atom, but if you look at the crystal itself, you actually put 2 silicon atoms in specific direction with specific angle that form the silicon crystal. So those are the bases for what we call lattice plus basis together to form the crystals. Okay, let's hold that. We'll come back and look at it. What we want to talk next. So here is a description for the crystal structure, right? And next we want to answer what is the bonding between the crystals. So bonding potentials, and what really holds the material together, I think I said this before, are charge. Right? It's the electron. So I say electron is the glue for all the materials. Okay? And when we have the typical potential, when I have two atoms putting close together, so a typical potential curve is this is the separation, and this is the potential, interatomic potential, and they always look like this, right? When they are far apart, they're attractive. And when they are close to each other, they are repulsive. That's a typical interatomic potential. And the minimal energy point is where the separation will be most stable. Right? So it turns out this why you have repulsive, that's when for example, the nucleus of the two atoms, positive charge, start to overlap, influence each other, and that's always that's what's the cause of repulsive. And nuclei, of course, that's when they get really close. Right? So repulsive part is actually easier to describe. Repulsive and typical potential form for the repulsive part as a function of separation. One is people often use is the 12th power law, very sharp function, 12th power, right? This is a lennard-jones type. And the other is using an exponential function, U0 exponential minus R Cassay. And Cassay is the characteristic length. And this is Born-Meyer. So repulsive, that's the typical form that people use to describe repulsive potential. And what really differs between different crystals is the attractive part. Okay? So attractive potential and I said the electron is the glue, right? So even for the least, strongly bonded crystal, it's still due to electron. These are the crystal formed by inert atoms. Argon crystal. Argon is a gas, right? But if you cool to low temperature, it actually forms crystal. So we already learned before argon why it's stable, because the atomic electron fell to the close to the, let's say, n equals which line it is there? I forgot. N equals 3, right? 3 or 4, okay, right? So it fills a closed shell, and there's no, so each neutral atom is neutral, right? So even in this neutral atom, remember an atom always have a nuclei and the electrons, right? So when you put them together, what's the interaction, why they could have attractive, is this positive nuclei will attract the electrons in the neighboring atom. And similarly, the electron of this atom will attract the nuclei in the neighboring atom, right? So these are the dipole-dipole interactions. So you will polarize, mutual polarize each other, and that creates attractive force. Okay? So this attractive force is a van der Waals. And the attractive is A to the separation 6 power. And repulsive is positive, attractive is negative. And so by putting the crystal together, forming an argon crystal, what we have is when they are very close, it's repulsive. When they're far apart, they are attractive. But of course, a real crystal has many atoms, periodic arrangement. So we want to, a stable crystal is when the total energy is minimized, right? So if I have many atoms together, I minimize the total energy. So if I have the total energy of the crystal, if I denote the atoms as say I sum I over j, right, pair-wise, because what I have here is between two atoms, so atom I and atom j, and sum up all the atoms, and I does not equal to j because I'm looking at the mutual interactions, and I have here the lennard-jones, that's a B Rij 12. Ij is separation between the two crystals. If it's a cubic, you can calculate no matter how far apart in terms of unit constant. And then minus Ba Rij 6 power, right? So you this is total energy, and when the crystal is stable, is you take the R12, for example. 12 is the unit constant, the constant between two labor atoms. You can always express Rij between further away in terms of if you have a cube, right? You can express any further point in terms of the smallest lattice constant. And you can take the derivative of that in terms of lattice constant, and that gives you where the crystal is stable, what's the corresponding lattice constant. So this is the simplest potential. That's the van der Waals potential. And correspondingly, this kind of crystal is called van der Waals crystal. Argon and krypton, those crystals are van der Waals. So I remember you see the Superman. There's this krypton, right? I don't know what's the condensate or the temperature. I haven't checked. What's the temperature? And it's not a very strong bonding. Okay. And secondly, what I say, let's look at it. This is where it's really the van der Waals attraction. And the next type of attraction that's easier to deal with is if you have salt, right? And in the case of salt, sodium chloride, what happens is the sodium, the electron has one sodium, has say one outer electron. You completely lose it to the chloride. So sodium is a positive charge, and chloride is a negative charge, right? And in this kind of periodic arrangement, you have attraction. If sodium, say, is sodium atom, is a positive, is a repulsion. It says a chloride atom is attraction, right? So at the end, whether you have a stable crystal, is you put all those energy together, you minimize them together, and in addition to the repulsive, you can't put them too close, right? So in ionic crystal, and the attractive potential for any atom I, attractive part is it has to be attractive. The lead effect has to be attractive. Otherwise, everything is repulsive. You don't have a crystal, right? So this atom I, you look at the surrounding sodium. You look at the surrounding, the next atom could be chloride, right? So you sum them up, and you look at the next shell, that would be sodium again. That's repulsive. And you do all this summation. So we have this summation of all other atoms. And if they are, say, charged, each atom is with charge Q, so plus minus to represent its repulsive or attractive due to electro-Coulomb interaction, Rij, right? So this is the Coulomb interaction. And it's very simple analytically. And again, you can express further atoms, say, in other locations. If this is the one you're considering, any other location in terms of unit constant. And so this one, in fact, sometimes people write into alpha square, alpha q square, 4 pi epsilon 0, and R0 is the nearest labor distance. So that's the nearest labor distance. And this alpha is a constant for different crystals. You do your structures, you sum it up, it becomes just dependent on crystal structure. And this is a Madeleine constant. Okay? So with this, and also with the repulsive part, you add them together, the whole crystal, you find out what's the nearest labor separation that minimizes total ionic crystal energy, and that's the stable crystal structure. Okay, so having said this, if you do your, this is of course the minimum. This is a 0 point. It doesn't include temperature, right? Some of you may do molecular dynamic simulation, for example. And in that case, the non-zero temperature, you write the F equal to ma, and your F is this kind of potential interaction. And that separation now is not the ideal lattice constant because the atoms jiggle around. So this separation was a function of time, right? And dealing with ionic force become more challenging. In fact, that's more challenging than covalent in certain sense, because this dies out very slowly, right? 1 over R dies out very slowly. And that means you need to include a lot of atoms together to do your simulation. Increase your domain size when you do a simulation. If the force is short range, it's much easier to simulate. Okay. So now we have ionic, and next is covalent. So I have given a covalent example before, and this is when 2 hydrogen atoms form a hydrogen molecule, right? So when we have 2 hydrogen atoms form hydrogen molecule, and the lower energy states is when now electron, because of the Pauli exclusion, the hydrogen atom energy level split into sigma and sigma star, right? Sigma bonds. The lower bound one is when the electron orbital is like what I drew here. And you can see the electron is orbited between 2 hydrogen and it has directionalities, right? And those are the covalent bonds. And if you form a crystal, so again, 2D for simplicity, so you have directionality in this one, you have directionality in here, directionality here. So these are the regions where most likely you find the electrons, right? And in this region, you don't find, the probability to find the electron is small. So the bonds has directionality. Right? Those are the covalent bonds. And now the next one is if this expand, start to overlap, and fill the whole space, those covalent, right? The electron can go anywhere. That becomes, under that picture, I come to the metallic bonds. Electron become free. It's a metallic bonding. So covalent is strongest bonding among the, say, for the crystals. Okay? And in person, when we deal with water liquid, there's also hydrogen bond. Right? What is hydrogen bond? And I think you all know. So if I have H2O, right? So I have, say, this is the hydrogen, this is the hydrogen, this is the oxygen. And it has some directionality in bond angle. That's a single water molecule. And now when you bring your next molecule, oxygen will form some bonding rather than just now electron is shared between one hydrogen, say H2O molecule. There start bond between this oxygen and next hydrogen. That's your hydrogen bond. Okay, so what I have talked so far is the periodic structure, crystal, and the basic notation of periodic structure. And then we talked about the bonding, what holds the atoms together, different forms of bonds. And then next, I want to come back to this periodic structure. I'm going to talk to you very mathematical concept. And this is a Fourier transform. And if you're an electrical engineer, you're familiar with the frequency domain, right? And the question is, we mentioned this in different occasions, like last time when we talked about the von Karman periodic boundary condition, right? So and last time when we talk about von Karman periodic boundary conditions, we say a one-dimensional lattice chain of length L, right, has n atoms. And von Karman periodic boundary conditions say x plus L equals cosine x. And from there, we use the Bloch theorem because this one is x exponential mass I k, which is the wave through the whole lattice. L is Na, and that equals cosine x. So this is the Bloch theorem. From this equals, so this one equals 1. That's why we get a k equals plus minus 2n pi divided by capital Na. So this is how we got, one way we got it, right? From Bloch theorem, allowable wave vector k. And the other way we got it, we explain it, is I just have a wave function here. I want to expand in Fourier space, right, in Fourier series. So these are equivalent. Essentially, they say I have a periodic function. I want to use, here is extended wave in Bloch wave. The other one, once you expand it into Fourier series, you still get a wave vector. You got the extended wave through the whole region. Right? This is 1D. 1D, I think you're all probably comfortable because it's just a corresponding time, right? Time into 1D space. Now I'm asking you to construct a 3D because the crystal is periodic in 3D. My wave function I'm going to write, in general case, a wave function at any location plus any translation of wave vector, that's periodic, right? Or unit, say primitive lattice vector, and that equals. So now I have a 3D, rather than writing 1D, can you do the Fourier representation, right? So this is why we introduced the reciprocal lattice. And turns out, if you look at the 1D, here, the period is A, right? And then in your denominator, you have A. So it's the inverse of that period. Okay? So the way I do 3D construction of that period unit vector, because the 3D, so a real space 3D is inverted into Fourier space 3D. And the Fourier space, I also correspondingly have a primitive unit vector, a primitive unit cell, and wigner-seitz construction. Okay. And the way I construct this reciprocal primitive lattice vector is if I have the A1, A2, A3 as the real space primitive lattice vector, and then the reciprocal space is B1 equals 2 pi, so that's my 2 pi. Okay? Length becomes volume. So length becomes volume. And here I have A2 times A3. And I permute the subscript, then I have B2 is 2 pi volume A3 times A1. This is across the vector product, and 2 pi way A1 times A2. And this ensures me that's the corresponding vector in the Fourier space of this 3D periodic space, real space. Okay. You will see why. Let me give a few more points. Here. And so with that, I can construct, this is my primitive unit vector in the reciprocal space. So the translational vector, so any of this M1, B1, and M2, B2, plus M3, B3, any of this combination give me 1 point, the lattice point in the reciprocal space. So this will make a periodic space, reciprocal space. And that's reciprocal of real space. It turns out, sometimes I joke, physicists live not in the real world, they live in the reciprocal world. Okay, that's because most of the time you see everything is drawn in terms of the wave vectors. And you can, of course, construct your unit cell, primitive unit cell, wigner-seitz cell based on this lattice points. And now, if you have your, for example, you have your function that's periodic, any function that's a periodic, r plus t. And the way you do your Fourier transform, if this is due to this periodicity, you can write this function in Fourier series, right? 3D rather than 1D Fourier series. Now you write 3D Fourier series. And the Fourier series is U r equals, and here is the Fourier constant, UG, exponential IR times G. So like R times K, and this is a sum up over all G's, over all those lattice points. Okay, and I will not say prove, but I will use that. I'll do that proof in the next lecture. The point of this reciprocal space, what you could use, it's very easy actually doing when you do an experiment. When you do a transmission electron micro, say, diffraction pattern, it turns out that what you map out are the reciprocal space. You can actually easily map out this reciprocal space. And so if you have object, crystal, periodic structure, right? You shoot a wave comes in, and you have diffraction, right? And some of you have seen gradients. How many of you have seen gradients? Gradient structure. So it turns out that any periodic structure, next time I'll bring one, okay? You should say light onto a gradient. You only see the diffraction, the light in the reflected in any in discrete spots. Okay, so again, if I have a periodic range of atoms, and what they'll say is only in certain directions, you'll see the light come out. Or this is not light. This could be electron beam when you do transmission electron micrograph, or it could be X-ray, right? Why you use X-ray? Because the X-ray wavelengths can be very short, comparable to the lattice constant. And in that case, say if you satisfy this gradient say condition, let me write down the condition. I'll prove it in the next lecture. So your condition is if this is the wave vector of the incident wave, this is the wave vector of the reflective wave, and you will have Ki minus Kf equals plus G equals 0. So you say G is the lattice point in the reciprocal space. Okay? And say this is incident, reflected. And coming back to why at the beginning we draw the electron energy dispersion. This is pi over A, right? And we only draw over pi over A. And this pi over A turns out that's the wigner-seitz cell boundary in the reciprocal space. Okay? So having said all this, I think we really need to look at some pictures. Let's look at the So this Google image is wonderful. I don't need to draw anything. Let's first look at the Bravis lattice, right? And you can say there are 14 types, right? Here is triclinic. Right, different angle, different lattice constant. And here, the simplest is a simple cube. This is a conventional cell. So if I put, say, a center here, put a lattice point at the center, then this simple cube, I got a body center, right? And then if I put a lattice point at every face, I got a face center. In this conventional unit cell, you can have more than one lattice point. In primitive unit cell, you can only have one lattice point. So if you look at the body center, how many lattice points I have? Equivalent. 2, right? Because each of this corner is shared by, say, 8, right? So that's 1/8. So simple cubic, I have 1. Body center, I have 2. How about face center? 4, right? Because say every face, you have 6 faces, and every face is shared by 2. So that's 1/2, and that's 3 plus 1 of the 8 corners. So gives you, so this is, if you look at they form a total of 14 type. And hexagonal is also interesting because a lot of people are interested in graphite, right? And graphite is a hexagonal structure. So let's look at so this is the Bravite lattice. Let's look at some real crystal structures. So starting with sodium chloride. This is probably easier. Let's still look at this here. Right? If you say sodium chloride, and here is, if we look at sodium atom, right? This is here at the center, you have sodium, right? So a basis is between here and here. That's say a molecule, you put the sodium chloride, and at every point you can look at that same sodium chloride, you repeat that basis at each lattice point, right? And look at the silicon structure. Silicon. Right? If you look at silicon crystal, what you have here, again, this is a face center. Right? There is one point here, but you have each point, you actually put 2 atoms silicon. This point and this point. This is not in any of this is 1/4, 1/4, 1/4 point. Right? So between 0, 0, 0 and 1/4, 1/4, 1/4, you're repeating that structure to each lattice point. So it turns out this atom there is more like a tetragonal. It's equidistant between this and this center and this center. Right? So it's at each lattice point, you put a basis. You put say a molecule or atom, say or 2 atoms of 3 atoms, many atoms. You can have polymers form crystal, and that could be a very large basis. Okay. Reciprocal space. Let's say, I don't like this. Wigner-seitz. Okay, so you can say this is a construction of a Wigner-seitz unit cell. So you have a point in the center. If you from center to this direction, you take the midpoint, you cut I think you cut this plane, right? So the Wigner-seitz cell looks in 3D, it could be very irregular, but that's a unique way for constructing. There's no ambiguity, and each lattice type you construct you can construct a corresponding wigner-seitz unit cell. So reciprocal, I still on Google. Unit cell. Let's say this. No. That's good. Do I have a simpler? Okay, so this is now getting more to what the people usually draw FCC structure, phase center cubic. They will say, okay, they actually have specific rotation from gamma to L. That's a 1, 1, 1 direction. Okay, and the way I look at this, the shortest distance is say because 1, 1, 1 is the longest distance in real space, and inverse is the shortest distance. So I'll say that's the 1, 1, 1 direction. This is the 1, 0, 0 direction, longest distance, right? And so those are the very complicated reciprocal space. And coming back to here, this is the broad condition. We'll prove it next time. I don't actually know whether it's a 1G or 2G. 2Gs? Let's see. Okay. So if you do your, you can map this out. So TEM diffraction. So if you do transmission electron microscopy, we mentioned TEM is you accelerate electron to very high velocity, and under that high velocity, the electron wavelength is short, comparable to the lattice constant. So now it goes through a thin specimen, typically 1,000, 2,000 Armstrong maximum, right? It goes through there, and even though it's 1,000 Armstrong, remember the lattice constant is a few Armstrongs. So you got 1,000 period. And so it's a periodic structure. And depend on, so you rotate your crystals, you can look at a different diffraction spot, right? In those dark region, you don't see the electron going there. That's a result of the wave diffraction. And again, we'll show this, we'll prove this later on. And that's the electron diffraction. Let's look at the X-ray diffraction. Right. So X-ray diffraction again is an optical wave, and what you people say is people they don't the image, the detector is typically a line. So by rotating the angle of X-ray incidence, you see the peaks, right? Again, that's the Bragg condition requirement. And let's see whether they're the clean ones, right? Some of this clean peak, what is? Oh, I like this one. Oh, doesn't look like I can show this one. Okay, so you can say so basically people have built libraries. And sometimes you don't even know what you have. You get all those peaks, you search a library, and you find out what the materials you have. Okay, and one more time, going to next time, I'm not going to go through this here, right? It's no longer a single spot. Why? That's because it's not a single crystal. It's a polycrystal. Okay, so you got the rings. So this is all coming back to the reciprocal space. You can rotate your crystal, rotate your angle of incidence in X-ray, change your angle of incidence. So you can map out what's the lattice constant, what are the arrangement of atoms. Okay, I'll stop here.